Afternoon, everybody, and welcome to this UKCCSRC workshop. This is one of a series of workshops trying to identify research needs. This particular one is looking at capture. A couple of points on the slide here of order. People are asked to keep your camera muted, camera off and muted during the presentations. If you'd like to ask a question, use the chat function, raise your hand. I'll be watching for that, and then I'll try and ask you to pop your camera on, unmute yourself, and ask those questions at the appropriate moment. The presentations, but not the open discussions, are going to be recorded. So while we are recording now, I guess at a certain point, Karis will stop the recording so that effectively the questions and thoughts are not uniquely attributable to any individual. So what we've got today is a series of presentations from different people talking about their projects, which will hopefully stimulate some ideas. So we've got Petrofac, we've got Wood, we've got Hume Zero, Net Zero Teesside, and the HSE. Then there's a break, and then we have the opportunity to try and capture ideas for possible research areas, try and prioritize those a little bit, and give people the opportunity to discuss those, potentially perhaps discussions between academics interested in doing research and people who might have research challenges, challenge owners, if you like, who have things that they would like to explore that might be suitable for academic research. So in terms of the objectives of the day, we're trying to capture research needs that people have across carbon capture and storage. Today is looking at CO2 capture, including post-combustion capture and hydrogen. So it's a broader definition of CO2 capture than we might have had a few years ago, but it's an appropriate one for today. And we're building on some work. If we've got one more slide, Karis, two more slides. Building on some work that's been done in the past around research needs that have been previously identified. And I'm not going to read the whole slide, but there is obviously ongoing interest in environmental controls. There's the interesting question of where do you draw the system boundary. There's dealing with waste and kind of risks of consequential environmental damage. And then I think we've got a couple more. We've got the challenge of smaller emitters. There's been a number of little bits of work done recently on how much CO2 is enough to make it worthwhile capturing it. The ever popular challenge of cost reduction and measurement and metering, particularly fiscal metering, I guess, in there, and concentrations. And then I think the final slide on previously identified needs, which any one of these may need further clarification. There's hydrogen technologies, there's a range of hydrogen technologies to look at. There's biomass, there's hydrogen storage, and then how do you retrofit these things to existing facilities. So those are kind of research needs that have been previously identified. Hopefully we can pursue those a bit more today. Maybe try and deepen our understanding of really where the boundary is between what's known and what needs to be known. Really try and identify down what research would be the most valuable for people trying to implement these. But before we get into all that, we've got these series of presentations, and I think the first one is from Petrofac. So I think we're ready to go to Chet.
Good afternoon, everyone. I'm Chet Buliok. I'm the technical director at Petrofac Energy Services. I'm pleased to present to you what I think are the research needs for carbon capture and hydrogen. This is based off experience of projects we've recently delivered or or we are currently delivering right now at Petrofac. Just a bit of information about Petrofac. We are an entity. We deliver energy projects. We beyond that, we also do O&M, train, operate and maintain. I also do some training. I'll skip through these slides pretty quickly and tell you about new energies, the arm of the business where I sit. We look at CCUS using our existing knowledge from oil and gas to do carbon capture and sequestration. Similar with hydrogen, we've been doing offshore wind for over a decade now. Waste to value, waste to energy, we do that as well, and then emission reduction, helping our existing clients to reduce our emissions. So now that that's out of the way, just a little bit about Petrofac. I'm going to go into some of the areas where I think research will be really good. I'm going forward, at least over the next couple of years. And the first area I picked is I went back to my academic years over a decade ago when I was doing research in CCUS, and that is design and operation of flexible or dispatchable and abated combined cycle gas turbine power plants. Previously, when I looked at this, I really focused on the design, trying to couple it together, looking at all the key integration points or connection points, which, in other words, these are energy losses or parasitic loads on the plant itself. At the end of the day, you can do other things to make it more efficient. But I think now with what we are seeing well, yeah, a week ago I was looking at what was on the grid, and gas was providing 40% of the electricity on the UK grid, and with net zero T-side going forward and our projects and SSC, and with the way the business model for CCUS is particularly power CCUS is currently shaping up, dispatchable power from combined cycle gas turbines that is abated, that with emissions abated, would be key, and this will be slightly different from a lot different from what we've been currently designing, which is very efficient, very tightly coupled. And so one of the things that I'm looking at is how do you manage that trade-off between flexibility and efficiency? What are the things you are going to look at? In the past, myself, I've been guilty of it. I've focused on building high fidelity models of the capture plant, modeling mass transfer and kinetics, chemical kinetics. But at the end of the day, when you look at the system overall and how it behaves, the main focus is the turbo machinery and the system hold up, really, particularly in terms of how you are going to run it flexibly. So yeah. So what should we be looking at going forward? Yes, back pressure gas and back pressure turbine is something that has been pointed out that will make it very efficient. Also rich solvent storage, storing your rich solvent and regenerating at the appropriate time. What kind of other operational sites can you look at? So there are a lot of things you can do. So I think one key area, particularly with the kind of projects that are coming up and be developed now, is really look at how you can run this plant very flexibly and ensure that they're able to maximize revenue from the business model that is currently being generated. So before I go into the next point, I'll just point out that this next research area, I think is a good focus, is something that came out of or is coming out of the work that Petrofac is going to do in the Stockholm Exeter project, where we are delivering a feed project for the capture plant and associated units, that's compression, liquefaction, and on-site storage for the combined heat and power plant. That particular project, one thing that has become, will I say, quite interesting in terms of the decisions that needs to be made is at what condition do you store the CO2 that you've captured? What condition do you store it, and what condition do you then transfer and offtake it? Perhaps in the UK, this is not such a big issue at the moment, but we expect that, for example, Acorn, which is at reserve status now, will probably move forward as well, and it has an import terminal. So when you look at what's going on, Northern Lights, which will be taking on a lot of CO2 from around Europe, the specification is medium pressure CO2. That's at around 14, 15 bar gauge, minus 30 degrees Celsius storage, and that's the pressure that is transporting. And if you look at what Acorn, particularly the import terminal, is shaping up, we're looking at lower pressure. That's about around lower pressure, maybe around 7 bar, and minus 50 degrees Celsius storage temperature. And I've seen other studies that has come across our way a few times. People are also looking at high pressure. What pressure really, or what conditions do you want to store and transport this CO2? Yeah, it's not necessarily capture, but at the end of the day, is the CO2 spec that you are generating at your site that you need to move from a far location to the storage site. And when you look at this study closely, it goes beyond looking at the OPEX of compression and liquefaction and CAPEX. You also have to consider the ship transport capacity and a number of items around that. And even when you are looking at CAPEX, it's not just different size of vessel, a bigger vessel or whatever. There's at the point where you can no longer use low temperature carbon steel. You have to switch to stainless steel. So how do all of this impact the overall viability of that particular storage or storage condition or storage or transport condition? So those are questions that really need answers as these projects are moving very quickly going forward. We've talked about, at least Jeremy mentioned hydrogen storage as one of the items I was pointing out last time. Again, this is critical, because looking at one of the projects that we did here at Petrofac, feed project, particularly not blue hydrogen, in this case green hydrogen, but it affects blue hydrogen as well, is that you need to store hydrogen, particularly when you look at things like energy storage, when you have to do curtailment and the like. You need days of inventory storage of hydrogen, which is not something that we normally do. Hydrogen is generated and used almost immediately. But if you are going to store this large amount of hydrogen, how do you do it efficiently? At the moment, it's only the salt caverns that we have that is efficient, but for large storage. But we can look at other means of doing it. So in the project that we did, we used to approach, we did cryogenic liquid, which is quite energy intensive. And we also used a line packing approach to store hydrogen on site. But again, how do you then store hydrogen efficiently and in a compact manner, particularly if you don't have a silent aquifer close by? You have, as liquid, cryogenic liquid, there's a lot of energy, high pressure gas. There's a lot of volume and a lot of space to which you need to store hydrogen. Are you looking at ammonia? Are you looking at methanol? Are you looking at metal halides? How are you going to store that hydrogen effectively, and what kind of numbers are we looking at? So again, in a similar way with what I mentioned with the CO2 transport, it has to be a full stage study. That means it's not just storing the hydrogen as ammonia, but what's the energy usage, energy cost in cracking that ammonia when you want to get your hydrogen back? So it has to be a kind of a holistic study to look at, and perhaps there are other means of storing hydrogen that are more energy efficient. Now, the final point I'll make as I come to the end of my point is hydrogen demand. There's a lot of focus on supply. Yeah, blue hydrogen, green hydrogen. Yeah, we are going to generate hydrogen. We are going to use it. But I'm sure some of you have seen this hydrogen ladder by Leverage and Associates. This is something I really agree with, because at the moment, when you look at the demand for hydrogen, the uptake is what we use hydrogen for at the moment, for ammonia, fertilizer, for hydrogen cracking in refineries, for methanol. When you look really closely, what other demand can use hydrogen for where viable alternatives do not exist? Not many. Yeah, so a robust market-driven study of hydrogen demand is needed, not just saying we are going to supply hydrogen. We need to be sure that, well, we need to show that it makes sense. As an engineer, I struggle with some of the numbers I see, and I'm hoping that going forward, it will be clear that there is that market, that demand for hydrogen, rather than a kind of, we build it, they will come kind of approach. I'll stop there, and yeah, I'll hand off to the next person.
Thanks, Chet. So I think up next we have Suzanne Ferguson from Wood.
Thanks very much, Chet. I think that was really interesting. I certainly agree with all of those points, particularly around the CO2 storage conditions when you're going to be putting the CO2 onto a ship. So far, we've seen all of those options proposed. From my point of view, coming from an LNG background originally, we'd assumed that low pressure, low temperature would end up being the most cost effective, as it has done for LNG. But we're increasingly seeing all sorts of different choices taken by clients. So I think that would be a really fascinating point to consider. So thanks for that. So I've just got a super quick overview of Wood, just in case there's anyone here who didn't know who we are. We came about when AMEC Foster Wheeler and the Wood Group came together. So we've got a really long history, and we've got a huge number of employees around the world. And we're split into 3 different parts within the organization, although we frequently work across all 3 at once. So we've got the projects operation, who will build a whole oil refinery in Saudi Arabia. We've got the operations organization, who run things like the CATS terminal on Teesside. And we've got the consulting organization, which is where I sit, where we can do anything from taking a blank piece of paper and coming up with a design when the clients have perhaps very limited idea of what it is that they wish to do, through to supporting FEED and EPC projects. So we've got quite a range of different ways that we are involved in the energy transition. We've done a huge amount of work in the carbon capture area, with over 145 different studies being executed, big benchmark projects, but also we've been very strongly involved in the UK clusters very recently. But we're also a hydrogen unit licensor. So we've got 120 hydrogen units that are producing grey hydrogen around the world. And that's been running for decades, that part of the business. But we're now pioneering new innovations in lower carbon footprint hydrogen generation. But we're also very heavily involved in wind and solar around the world as well. So we've done all kinds of different projects that quite often have different interactions between the elements of decarbonisation or elements of the CCS chain. But I won't dwell on these for now. But a project that I wanted to mention that might be of interest from hydrogen and a post-combustion CO2 capture point of view is the Hume Zero project. But I'll go through it briefly because I know Mayowa is on the line and he knows far more about it than I do. This is a really exciting project looking at creating a low regrets pathway to rapidly and cost effectively decarbonize the huge industrial cluster up on Teesside, up on Humberside, that is based around Immingham, where you've got 2 oil refineries, a power station, and various other really significant industries that are going to be challenging to decarbonize. So the project was looking at how you can use synergies across different sites to, say, take an excess fuel from one site and put it into a power plant on another site with post-combustion, and then generate hydrogen and use that for decarbonisation on a 3rd site, for example. So some really exciting interactions, but it led to a great many questions in how the best to design systems that can have so many variables. So I'll come to that hopefully in a minute. Another really exciting project that we did last year was to come up with an energy transition master plan for SGN, who wanted the scope of their project was to look at decarbonising 80% of the gas grid in Scotland. So pretty broad. That looked at who's going to be the hydrogen users, who are going to be the people that are going to need to use post-combustion carbon capture and can't decarbonise with hydrogen. What are the people, the sectors of the industries and society that will be more likely to choose electrification, like vehicles or small passenger vehicles, for example, and to pull all of this together to say what will the hydrogen demand be like by 2050, 2045, mostly is more important in the case of Scotland because that's when they have their net zero target. So this also raised a huge number of questions, not just about CO2 capture, but also about hydrogen with CO2 capture. And when we're blending blue and green hydrogen, what are the differences in the markets that they can supply? And then also last year, we were very fortunate and grateful to win 2 lots of the UK's hydrogen supply programme for BEIS. So this enabled us to do some feasibility study work, looking at taking that hydrogen technology that we've had for decades, that of course, being a grey hydrogen technology emits 10 tonnes of CO2 for every tonne of hydrogen you make, and to transform that into a technology that is fit for a net zero world. So of course, we've modified the flow scheme to come up with a blue hydrogen flow scheme, which has got integral CO2 capture rather than post-combustion on the back. But also, can we change that into a biohydrogen technology? Can we put bio feedstocks into our reformer, and what are the potential for making biohydrogen that's carbon neutral, or potentially even putting it into the blue hydrogen flow scheme, which would make carbon negative biohydrogen. So that was a super exciting project, but again, led us to have lots of questions about market implementation, requirements for purity. So I've tried to capture some of those here. So particularly on CO2 capture, of course, I'm sure everyone will be aware that there's been this long-running debate about proprietary versus non-proprietary solvents. And we are frequently asked by clients or potential clients about open art solvents and whether or not we would consider them as a demonstrated technology that could be used by 2025 or 2030 and where they've got to. So it would be great if we were armed with better data so that we could perform more strong designs. So of course we can take MEA at various concentrations, we can model it in HYSYS or Promax or any of our processing software. But the things that are very difficult for us to predict are things like what will the emissions be from the absorber, from water wash stages, acid wash stages, how effective are demisters, things that are really much better done through lab testing and on-site testing than we can do through our simulators. Because if a company like Wood is to deliver one of these units, we need to be able to provide a performance guarantee for how well we can make sure that we have got rid of any emissions that could be harmful to the environment, as well as what would the emissions to water be? Because quite often, if you, for example, you've got an acid wash, that might reduce your ammonia emissions that are coming from the absorber, but then you have emissions that would go to water. Instead, you need to make sure that the environmental implications of your water treatment isn't outweighed by the environmental benefit of having used the acid wash on the absorber. So what we really need is test data for these potential open art solvents that can use us to design, that can help us to design and operate a really robust plant where EPC contractors or anyone else who wants to become a CO2 provider, CO2 capture technology provider, could then use this data to build robust plants. And that includes things like solvent degradation, which is also frequently something that as an engineering company, we would expect licensors to provide a guarantee of. And things like corrosion rates. What is the Caesar solvent like in terms of corrosion versus any proprietary solvent? What are the implications on material selection? How thick do we need to allow a corrosion allowance? And these are things that are really difficult for us to find data on at this stage. So whilst we might well be able to, with good accuracy, model how much steam requirement there might be for the regeneration, what we can't model accurately is what the solvent degradation is like over a period of several years, because the data, as far as I'm aware, is not available. I would just like to caveat, it's been a very, very hectic couple of years. I haven't necessarily kept up with what research has been coming out, so I do apologize if any of this is already out there, and if there's anyone listening pulling out their hair saying, I published that last year. Sorry, I would be very interested to see it. So the next one I've got is about emissions from the absorber. Obviously, this is a crucial concern for everybody from an environmental point of view in particular, but also from a solvent loss point of view, it can be very important. But it can be very difficult when starting a project to know what the limits actually are, and to be fair, what the limits should be, because some of the research that's been done at TCM, for example, has looked at how much amine has ended up in the environment, and they're finding that actually there was already more amine in the environment than they could detect an additional amine because of the project, if that makes any sense. So what should our emission limits be, and how much do they vary from one place to another? Because if you're designing a project that is in a location where there's already quite a lot of industries who are already having some emissions that have been allowed by the Environment Agency, the chances are the limits on your new plant will be very strict, which could be quite limiting compared to another location, for example. And we've had that example with ammonia on Teesside. But it's also important to understand what appropriate limits there are for SOx and NOx. So of course, when you're doing post-combustion CO2 capture, you're reducing the mass of your stream that you're emitting to the environment, which will increase the concentration, although not the quantity of SOx and NOx. So it's important to understand what the limits are and how we can make sure that we're always below them. And then also one of the points in the debate about proprietary versus non-proprietary solvents was something that as a non-environmental permitting specialist, I didn't really follow, which was the argument that there wasn't a purpose in disclosing every component as named to the public register, because data on the environmental impact from some of those components wouldn't have been known. So therefore the public wouldn't have been able to judge what the environmental impact of component A was, because the data wasn't available to them. So you'd be better to use pseudo components that they would be able to understand the environmental impact of, which to me highlights that there's a gap in the data that's available to the public, which perhaps might be a separate issue that we need to address as well. Then we've had lots of fun talking about CO2 emergency venting, and on the very odd occasion finding a project where we've done due diligence to find that there is no CO2 venting in the design, which is obviously something that needs to be rectified immediately. So when CO2 is vented, of course, there's potential, depending on how it moves across its own phase diagram as it's let down, that it could form snow, it could plug up pipes, or of course, ultimately, the crucial thing is to make sure that you're not going to do any harm if there's an emergency situation and because of the asphyxiation potential. But making sure that we model CO2 properly is absolutely vital. And it can change quite a bit depending on the amount of impurities that are in the CO2. Just 2% hydrogen in the CO2, for example, can have a huge impact. And we need to make sure that we know exactly how that CO2 is going to behave in CO2 emergency venting scenarios. Some really interesting work that we've done in the last year or two has looked at how to minimize the inventories that could be vented. So we'll have less flow of stuff being vented, but to make sure that we've properly understood how we need to manage that venting to do it in a safe way is something that we need to ensure our models are capable of achieving. And I'm talking about the thermodynamic models that are inbuilt to the modeling software. So I think we could really do something interesting to make sure that we're doing that in as a robust way as we could do, accounting for the impurities in CO2. Then we're also really frequently asked about CCU and how utilization technologies are coming on, especially people who are new to CCS and who are looking at it for their plant for the first time are always keen to understand if they could make a saleable product and why they can't from their 1 million tons per annum of CO2. And this is something that we periodically asked to look at, but if we don't have a project ongoing, then we don't have a reason to go out to go and get information from all of the novel technology providers to see where they've got to with their process. So it would be great if there was some sort of forum that's presenting where they've or a side-by-side review of the different technologies and their markets in the UK, either as a high value product or a high volume product that could look at taking a bite out of the amount of CO2 that we're going to need to sequester. And then to move on to hydrogen. Again, hydrogen purity requirements are really important, and they will impact on how much energy and how much capex you spend on the design of your plant. For example, there's very different hydrogen purity requirements at the moment for a vehicle recharging station for the hydrogen fuel cell vehicles, than there is if you're going to use your hydrogen to blend with natural gas or with refinery fuel gas for reducing the carbon footprint, rather than a full switch to hydrogen. So it's useful to look at what are all the different purity requirements and how they impact on things like the materials of construction that can be selected for infrastructure, what the fluid flow impacts are of impurities in hydrogen, because they can be really significant, and also what the carbon footprint of those impurities might be. Obviously, if you've got a 2% nitrogen in your hydrogen, then that's not impacting your carbon footprint. But if it's 2% methane, then it absolutely is. Then another question we come across quite frequently is the understanding, and Chet very rightly pointed it out, that it can be very difficult to work out the best way of storing hydrogen. And while some geographies have salt caverns or the ability to create salt caverns, many do not. For example, the whole of Scotland does not have identified areas where they could build salt caverns. So how, across the whole UK, how much storage do we think we're going to need? Are we going to be needing to repurpose gas storage facilities like Rough? Or can we do it all with salt caverns? These are some really crucial questions that I don't think I've seen answers to in the last 12 months. So how much storage are we going to need across the UK to meet things like the winter peak heating demand? When are we going to need them by, and where can we put them? Are all questions that I don't think I've seen spelt out, at least not lately. And then another point which comes up quite often is there's various different vectors that have been identified, and Chet also spoke about some of those. And we have a continual need to make sure that we're decreasing the energy penalty in how we produce those hydrogen vectors so that we can transport it over long distances economically. But what's also important is that one of those vectors is obviously the production of ammonia, and ammonia in liquid form is a much higher energy density or hydrogen density than liquefied hydrogen is. But there aren't really any processes available so far that are tailored to flexible operation. So this is really a green hydrogen question, but it forms a crucial role in part of the total hydrogen economy. So we need to have green hydrogen just as much as we'll need blue. And we're going to need processes for making that hydrogen that can easily ramp up and ramp down to match PEM electrolyzers that are tied to a wind or solar plant, for example. And that's because we're going to, the current technologies are very high temperature technologies. So you've got, for example, fired heaters with refractory bricks that aren't going to want to turn up and down quickly and be off for long periods and then suddenly switch on because they'll crack. And you'll need to replace the refractories all the time. So you get really poor availability. So any novel process routes to ammonia that can get around that will, I think, be extremely fascinating. Whilst the philosophy of a ladder of the use cases and the general idea of some being more obvious than others, I have so much to argue with in this specific ladder. when you start looking, when it says, for example, that it's uncompetitive to use hydrogen for system balancing, and it comes in at F, I'm afraid I'm going to have to disagree with that one. But as they're ranked in relative to each other, it's probably not far off. But they are all going to require usage, and it's really important that we understand the carbon footprint of all of these. So I'm sure a number of people will have seen the very controversial article that was published about this time last year that said hydrogen was worse for the environment than coal, or words to that effect. At Wood, we did, within a few weeks, put out an article which took apart this the analysis and pointed out all of the assumptions that had been used to snowball into a really unrealistic conclusion from the use of selective assumptions. But it would sound much better if it wasn't coming from a company that had a clear vested interest in producing hydrogen. So I think it'd be really useful, certainly for the public, but also for those of us who are involved heavily in the hydrogen supply chain, to see a really independent review of the carbon footprint of the different ways of making hydrogen. So I'm not talking about the benefits of ATR versus SMR, I'm talking about blue hydrogen when it comes from natural gas from a low CO2 field, what's its carbon footprint compared to when it comes from a high CO2 field, when that field, the gas treating facility might have CCS or it might not have CCS. So we might have, and then the true carbon footprint of green hydrogen or biosourced hydrogen, and perhaps even a side-by-side comparison for specific use cases. So if you're going to decarbonize domestic heating, what is the carbon footprint of your heat pump per unit of energy being used compared to if you are using green hydrogen or blue hydrogen for that same use? Because often we see things that aren't compared properly side by side. And I think that would be really valuable. And I think that is my last one. I'd hand over, yes, to the next speaker.
Thanks very much, Susie. Perfectly on time. So the next section is from Hume Zero. So we have Mayowa and Adam, I believe.
So the name is Mayowa Akinrinlola, currently a process engineer with VPI. And as you can see in the plan, that we're going to be speaking on 2 projects, and I'll tell you why. So that's where I've got myself and Adam, who will be speaking on the other aspect of the Hume Zero project. Yeah. So Hume Zero. So what's Hume Zero? Is Hume Zero a project? Is it not? So Hume Zero is more than a single project. So it's a set of projects, yeah, within the Hume region, and we aim to decarbonize the world-scale industrial cluster, yeah, comprising first the VPI Immingham CHP plant and the refinery, which is operated by Phillips 66. That's the Humber Oil Refinery. Yeah. And so because it's a set of projects, today we're focusing on 2 of those projects, yeah, which are very in very advanced stage of development. Susie touched on some of them around the hydrogen and all of the other projects that are currently in the pipeline, but we will focus on these 2 for today. Right. So VPI is developing the post-combustion capture on the CCGTs, which is one of the biggest CHP plants in the UK and in Europe. And Phillips 66 are developing a post-combustion carbon project on the back of the FCC, and that's going to capture up to 0.5 million tons per annum. But there are other aspects of the project that will make that number to go up to 1.5 million tons per annum, notably around the calciner. So between VPI and Phillips 66, these 2 projects are currently being developed and advanced stage as well. Yeah. Very quickly, let me just give you an overview of the VPI Immingham plant. As you can see, we've got 3 gas turbine machines. 2 of them are within the scope of this project, and those are the ones that are highlighted there, GT1s and 2, and also the 2 auxiliary boilers which support those 2 assets. And the project scope is built around those 4 critical asset, the GTs and the aux boilers. And very quickly, I'll show us what that scheme looks like and in the next slide. So as a scheme, we are proposing a capture plant train on each of the gas turbines. And so it's around 1.4 million tons per annum each, and 500,000 tons per annum on the 2 aux boilers. And those 3 trains can then, are combined into 2 trains of compression and dehydration before they then go into the transport network. Now, as I said, this is the scheme as it currently stands, but obviously we still continue to work on this, and it's very possible that if you speak to me in 6 months' time, I might present a different scheme. Not terribly different from this, but it could be different. Yeah. Now, within the time that we've decided to, talk briefly around the key project features, and hopefully, identify some of the key challenges that we see in the project. And those challenges can then, can be turned into research or focus areas. So first, let's go through the key features of our project. So first is an amine-based post-combustion carbon capture technology. We see steam integration and condensate return as a key aspect of this, because this is a CHP plant. So that means there's a base load production of steam, which goes to the 2 refineries, the Humber Oil Refinery and the Lindsay Oil Refinery. And integrating a capture plant means there's another big consumer of steam. And so we have to integrate all of this steam into the design. There's flue gas integration. In the earlier picture of the plant, you will have seen a big stack in the middle of the site, which is where all of the flue gas is kind of routed to the atmosphere. And so bringing the flue gas to the capture plant means we have to find a way to tie in the duct to the stack. And because there are 4 stacks there, we need to find a way to kind of tie all of those together and commingle flue gases where necessary to be able to deliver safely to the capture plant. Now that's a key feature of that design, and it's a lot of engineering effort to get that done correctly. It involves designing and controlling the flow of the flue gas. We're looking at equipment rationalization. Currently 3 trains, but as I said, potentially we could go to a 2-train solution if we're able to manage that. There's a lot of capacity changes that will arise as a result of implementing the capture plant. So for example, if we take steam from the existing steam header, we're going to reduce the cooling demand on the cooling water system, and so freeing up capacity there could then be used elsewhere. So we are doing a lot of study to understand what capacity changes will have to take place and what we can reuse within the existing capacities as well. A common challenge for large-scale carbon capture plants, the absorber, the blower, the regenerator, the compressors, all of these are very similar on large capture plant projects, but nevertheless, they are still there, and we're looking at them closely as we go through a FEED design. So challenges which we think could present some research opportunities. Some of these are common, you will have heard them before, but maybe there's some that might be coming out for the first time. This is what we're thinking. The first one, I think Susie mentioned this earlier, which is around modeling of the dense phase CO2. We see the prediction of risk contours, for example, when modeling unintended release of dense phase CO2. In the presence of impurities, we ask ourselves this question: have we got the right models? Are they predicting the contours correctly? Are we grabbing too much land than we need? Or are we just using too little land? Are we getting it right? Our current tools the right ones to use when we have impurities in CO2. So doing something along those lines and making sure we get the confidence that these tools are predicting the contours correctly. Measurement, online measurement of impurities in dense phase CO2. We have very strict TNS conditions to meet in terms of the purity of the CO2 and some of the entry conditions as well. So we need to monitor them. So we need to be able to determine that we can, correctly measure impurities in the CO2 online, like almost real time. So we will be able to take responsive action to be able to either divert the flow or take corrective action to bring down the contaminants. And the question is, have we got the right capacity to do that in terms of the availability of equipment? At very low concentrations, if you look at the absorber outlets, again, the same thing. You have very low concentration of some of those impurities. Do we have online tools to measure them? Do we need to do something more in this area to be able to give ourselves the confidence that we can deliver? Pipeline integrity is something that's come up lately, introducing new equipment into the battery limit of the emitter, which is to get down to some low temperatures. Are we over designing? Are we specifying temperatures because we want margins in there? Are these margins too large, too small? Having been able to predict this correctly would help project cost a lot. Now, all of the questions around the amine itself, my view is we've got a lot of test results that are supporting projects actually carried out on a very short duration. And because of that, it's very difficult to predict long-term, performance of the absorbents. Yeah. So the question is a demonstration project necessary to be able to get to a point where there's confidence, especially around open access amine, where there's enough confidence to be able to, to attract financial investment for commercial projects. And are there non-proprietary or non-amine alternatives out there? Is there enough research in this area to kind of identify other alternatives other than amine absorbents in the first place? Again, one item that is important, which is corrosion. Again, it's tied to the long-term performance of amines. Corrosion could become a problem when you look at what's being offered by different technology providers. You notice a big difference in the sort of materials that is being put forward. It's not consistent, even though they're all amine products. And so, are we getting this right? Because we literally don't have any plant that's that's been out there for 20 years or more. Just something we can do in this area to bring confidence that the right materials has been selected for projects of this nature. And I think that's it from me. So I'll hand over to Adam, who's going to take us through Phillips 66 refinery.
Yeah, thanks very much, Mayowa. So yeah, my name's Adam Wharton. I'm the process engineer on the decarbonisation team at Phillips 66. So the refinery is based in the Humber region. We employ over 1,000 people. We're unique in Europe for our ability to produce graphite electrode battery coke, which we're continuing to invest and increase production of to provide for the emerging electric vehicle battery market. We're the UK leader in the production of low carbon liquid fuels and the only domestic provider of sustainable aviation fuel. And that's through our processing of renewable feedstocks like used cooking oil. And we also have a roadmap to reduce our refinery emissions, which firstly sees us working in a consortium with other partners to develop our Gigastat project to produce green hydrogen for the refinery, where we can hopefully refuel various fired heaters. And most pertinently to this is the Hume Zero project, which Mayo has introduced, which from our part, we are looking at initially a carbon capture unit on our fluid catalytic cracker. There are other sources around the refinery, but we've selected that one to start with. It's the largest single source emitter. If you wouldn't mind moving the slide on, I suppose our sort of research opportunities are kind of broken down into the demonstrated, I suppose, by the challenges that we've sort of faced so far. Many are the same as the ones that Mayo has been through, but there are additional ones that need to be considered for when you're integrating a carbon capture to an existing or any existing industrial unit. So flue gas composition will be different depending on what the industrial unit is. It's important to have accurate knowledge of that composition, all the different components and contaminants to understand how they're going to affect the amine degradation rate, and also the propensity to form aerosols. And understanding that would then help specify the extent of pre-treatment that's required for each particular industrial unit. As an example, a key feature of the FCC flue gas is the catalyst fines, which we currently knock out the majority of them with existing kits to below environmental limits, but it's still not sufficient for a carbon capture unit. That's what we've found so far, so additional treatments required. Affected safety systems, so when you're applying a carbon capture unit to a refinery, the emission points may be spread over numerous locations, so it may require a single carbon capture unit to process the flue gases from a number of different units. And if that's the case, then it's a challenge on how to ensure that the safety systems are in place to adequately protect all the different emitting units. So our FCC unit flue gas, we also want to combine with 2 fired heaters, but because fired heaters run at a slight negative pressure, they need absolutely protecting from any modes of operation or any potential trips of the carbon capture unit. Any energy integration, so each industrial unit may hold opportunities to improve the energy intensity of the carbon capture unit. So it will be useful to know for each different potential industrial unit how that can be integrated. Our FCC flue gas operates at a slight elevated pressure before it's currently knocked down to the stack, but we intend to utilize that elevated pressure to remove the requirement for a bit of rotating equipment, a fan, so we don't need to push through the carbon capture unit. So that would help reduce operating costs and improve reliability. And the final point, again, is reliability. Reliability is key for us. So the refinery operating units have a fixed shutdown schedule, and so we need that carbon capture unit to operate trouble-free for that same duration. So it needs to be aligned with the with that operating unit. So it's important to really understand the weak areas within the carbon capture unit, so that they can either be designed out or mitigated against. That's all from me. Thanks very much. Could I hand over?
Thanks very much, Adam. So I think next up we have somebody from Net Zero Teesside. I guess it's you, Alex, as you've popped up.
Very good to see a lot of familiar names. My name is Alex Tate. I'll give it a bit of an intro as to what I do in a second. But just to start with, I work for BP. BP is the operator of the Northern Endurance Partnership, which was successful as part of the East Coast Cluster in the phase 1 process in terms of getting a kind of transport and storage regulator on the go. So that's really good news for us. We also, as BP, operates Hydrogen Teesside, H2 Teesside, and Net Zero Teesside. So on the capture side, I'm going to speak specifically about Net Zero Teesside Power. So that's the power station that's going to be co-located with the Teesside infrastructure. Will produce roughly 2 MTPA at the peak. It's a greenfield CCGT integrated design, and I sit between, so I work in as a project lead, managing or some sort of coordinating some of the interfaces between two feed contracts, which we set up in December of last year. So we were really delighted to just kick off two feed contracts last year with one with Technip, GE, Shell, and Balfour Beatty, and another with Aker, Siemens, and Doosan Babcock. So we have power OEM, licensor, and engineering contractor and construction contractor on board together from the start, working these two feeds. The dual feed, they're working in parallel at the moment, and I'm sitting sort of in the team, in the central team that's managing those. So there's a lot of work ongoing as a project. I would say from the start that we have quite an extensive technology qualification process and plan. And really a lot of that now is work that the engineering contractors are working with suppliers and others to qualify that technology ready to support a financial investment decision next year. So I won't go through the detail of the process, because it's become quite apparent to me that everyone on the call is far more knowledgeable and experienced than I am in this area. So I'm going to assume that you all know the sort of rough way that our project works. And I'm actually just going to focus, in the interest of time, on this one slide. So I've put together some of the key technology areas that apply to the capture plant, and some of the needs that we've identified that we may want to be doing, particularly over the next year. And hopefully this helps you identify where the kind of critical research needs would be. And actually, it's really encouraging to me to see a lot of alignment across the four speakers I've seen beforehand. So, Chet talked about the need for dispatchable power and the kind of intricacies that come up with that. I'll talk about that. Mayowa and Susie as well, talking about aspects that will come up quite frequently here. So I'll work through these. The first one is kind of repeating some of the previous stuff that we've talked about in terms of scale up. So we recognize there's two large scale coal facilities that have operated, that have good experience. But with a natural gas, flue gas, obviously there's a very different technical setup. And for us, there's a lot of work to do, particularly around the blower and the diverter, and actually the absorber as well. So we expect there'll be a lot of technical qualification to be done with the suppliers. I've listed a few things that we'd be looking at doing there, and I'm sure there's potentially some interest on that amongst this community. And equally, again, something that's well recognized about getting good gas distribution across what will be some of the largest absorbers of their kind. So there may be some work that we need to do in terms of CFD modeling on that. Something that I don't think has come up so far is specifically in relation to O2 removal and dehydration technology. And actually this links in very strongly with an integrated specification for the CO2. So we found that the O2 spec is really driven by the well design as well. So, with building an O2 removal unit into the actual capture plant, it may be something that we can design out through metallurgy downstream. So there's an integrated approach there to materials testing. And some of the reasons that we think this is quite an important area to focus on is driven by that dispatchable operation. So this start-stop technology that usually on a chemical plant or elsewhere in LNG facilities may run, or gas processing may run permanently. So there's a real shift towards the value when operating only when there's value to do so. Fluid characterizations, I think, has come up or has been inferred in a lot of what's happened already. So equations of state fluid characterization is going to be really important for impurity analysis and modeling across the facility. I think this applies not just to capture, but across the whole of CCUS. And I know that's an area that's received a lot of interest recently. The last three are probably where sort of the bulk of our focus will be. And actually, I think the bulk of some of what I've heard already will be as well. So on the capture plant, qualification testing, Mayowa already referred to the kind of length of testing that's done, the ability to understand some of the degradation products. I know that's a bit of particular interest to a number of people on the call. Things also like material impact on that for higher corrosion rates, which may well be something we observe, and reclamation technology, solvent management strategies. That's an area that we're going to actually lean a lot on our licensors to demonstrate to us as part of this dual feed that we're now in process. And then on the system integration and dispatchability, we carry this as well as across the full chain, but specifically within the capture or the power and the capture plants. We've completed some feasibility testing, mainly looking at startup and shutdown and how to kind of optimize the start sequence there. There's a lot more that we could learn around that area, and it's a real critical area of optimization on the project at the moment. one of the things we haven't talked about, and perhaps this is the wrong forum, but really it's letting the value drive where we do the research. And for us, that value, when you're dealing with a product that changes price every half an hour, is very, very heavily integrated with how the overall power dispatch market works. So I just had a quick look, and actually, unusually, wind is the highest producer of electricity right now, possibly because of the windy weather we're seeing outside. But there's a real, perhaps a lot we can learn and drive that value of research by understanding really when and how the characteristic of operation will change over time. So we've spent a lot of time looking at that, and that's something we continue to work at. Material resilience for mechanical and thermal fatigue. We've recognized obviously lots of starts and stops on big equipment that's perhaps not initially designed for this is a real area we're looking to demonstrate resilience for. Emission control systems, I'm not going to profess to know anywhere near like what I've heard already. So I think listen to all the previous presentations for that. And then also the simulation. So bringing together this full chain, it's not just to get to the details of transient operations, but things like optimizing our start sequence and to test how that is all integrated. And then the final thing I would say is about dense phase. It also does apply to gas phase to some extent for us, fiscal metering. So trying to engage with the suppliers to make sure we've got the right technology to achieve that. And I think this community is a really interesting one to talk with. I mean, I speak as an operator here, but we are working with a supply chain, and I know a lot of you represent engineering contractors or even perhaps people in licenses and suppliers. There's a real integrated approach to demonstrating this, and it all plays into, I think, some of the overall research needs that Jeremy you listed at the start, things like cost reductions, and I think that is really critical. So hopefully that provides a bit of an overview as to what Net Zero Teesside is focusing on with the capture plant. Happy to answer any questions later as we go through, but with that, Jeremy, I'll hand back to you.
Thanks very much, Alex. So I think we've got one final presentation from Simon Gant from the HSE.
Okay, so there's just one slide, so this will be pretty quick. I guess some of you would have seen in the programme that we're giving a slightly longer presentation tomorrow, but we've got these 5-minute sessions in each of the meetings this week. And part of that really is to try and re-engage with the CCS research community. HSE was pretty heavily involved in CCUS stuff up until about 2017, just after the government cancelled those competitions. And then we sort of withdrew from the community. So yeah, we're trying to get back up to speed and understand what research has been going on in the last 5 years. To look to see whether some of the knowledge gaps that we were aware of at that time have been filled, and to see what other knowledge gaps may have arisen along the way. And our focus previously was largely on the pipeline transport aspects of things. So it's been really interesting listening to these issues today on the capture side, and we're hoping to learn more as well later on the utilisation and storage side. So my background is on the science side. I was involved in things like cool trans and CO2 pipe has, but I'm not on the regulatory or policy side, and some of you here may have got questions on HSE's approach there. So there was a presentation given by a colleague, Trevor Sexty, at a CCSA meeting last year, and that does set out some of those regulatory policy side of things. So if you're interested to learn more about that, please get in touch, and I can pass on the presentation that was given there. So like I said, I'm on the science side. There's some colleagues that are also going to be attending these meetings this week that are more on the regulatory and policy side, so the contact details are there. And that was really it. But yeah, I'll hand back to you.
Okay, thanks, Simon. So hopefully the people will keep up to date with what the HSE is saying throughout these workshops. Karis, I think that takes us to the break, and then we come back to the Jamboard activity. We're just about 5 minutes behind schedule, so should we come back at 3:15, or do you think 3:20? Which how do you feel?
Yeah, happy to come back at 3:15. Gives everyone a chance to have a short break.
Yeah, I think that's probably enough time to grab a cup of coffee. So we'll recommence at 3:15 with the Jamboard then.
Sounds good. Thank you.